Let us see associative mapping. In associative mapping, the simple rule is any main memory block can go to any cache block. Okay, such a way we plan. So that what happens, so that we will be effectively utilizing the cache. But what are the consequences we will see? First we'll see with one example. Let's say you have 4 cache blocks 0, 1, 2, 3 and 8 main memory blocks as usual. Then these are the and assume that let's say each block has 2 words, and I am assuming that my memory is word addressable at this moment, okay, so that it will be easy for me to explain you the things. So we can extend it to byte addressable also, not a problem. First think about word addressable systems. Now there are 16 words, right, because each block has 2 words. Then 16 words are represented by 16 binary addresses 00000 to 4 ones. Now these two represent block number 0 in that way. So this block 0 is identified by last 3 positions you see. 001 means block 1, this is block 2, block 3 in that way. So last 3 positions identify the corresponding block number. Now there is no mapping now, I can say. Anything can go to anything, right? That's why there is no cache index. So generally in direct mapping we had 3 divisions, right? One is word offset. After that immediately we had cache offset or cache index. It depends on the number of cache blocks. This time we are not mapping one particular block to one particular block, then no cache index. Directly everything is tagged. What are we going to do? I will tell you. Example, let's say currently you have decided to keep this block number 0 of the main memory somewhere. Then what we do is we just go to randomly some memory locations. Example, I fix this cache block 0. I write W1, W2. That means currently this block 0 of the main memory is available in the cache. Okay. Now immediately there will be of course valid bit. I don't show the valid bit here for easy understanding. Let's only use tag field. Okay. So how many bits will be there in the tag field is 3 bits. That will be 0, 0, 0. Now you see. So 0, 0, 0 block of the main memory is now in this cache. So that's easy, right? Now, example, whenever you keep this data, this block, you know one thing, right? Always in the cache, we keep a block rather than a particular word. Though you want to keep this particular word in the cache, then we keep total set, right? Example, let's say you want to keep W11, W12, then what is that block number? 5. So that means 1010, 1011. We keep that W11, W2 anywhere, not a problem, which should be free. Then what should be the tag field? The tag field this time should be 101. This entire remaining thing is tag field. Now, example, let's say I am searching. How I search, you see. Suddenly you thought of accessing the memory. Okay. Now this is your random memory address 1010, 4 bits. Okay. Now this is your processor. How processor is going to access the memory, you see. First it will check the cache. In the direct mapping technique, what we did, we divided into 3 parts like this and like this. I said this is cache offset, and we thought, and that is a rule of course, in direct mapping technique, if and all if this word is located, that will be in the cache block of 01, cache of 01th block. That means one block, block number 1. But here there is nothing like that, so it can go anywhere. There is no cache offset. Directly we will take 101, right? Now we'll search every tag, because see, this memory word can go anywhere. If it is anywhere means any cache block. We don't know, then we have to search. That's why use this tag 101, search here. 000, no. 101, yes. That means what? Definitely 1010 is present in the cache. If you have a doubt, you check it out. What is 1010? 1010 is nothing but W11. Yes, W11 is available. Sir, we have a question. What is that? Somehow you identified the block, right? In that there are 2 words. How do you know that this is W1 or W11 or W12? We have this bit, right? What we do is this entire cache block will be taken. Okay. Now we selected this block. Since this bit is 0, then this, this word will be selected. Such a way we design our circuit. Understand? So this will decide that. Understand? Now one more example. Example, let's say, so this memory word, okay, 1110. So your processor has decided to search for a memory word. That means it wants to fetch a memory word called 110, 1110. So first we check here, tag 000, it's not 111, right? These 3 bits. So here 101, it is not 111. That means miss. So we say cache miss because that data is not available in that way. So associative mapping will work. But if you see the problem, so did you remember in the direct mapping technique we used only one comparator. So here also if you use one comparator, then what happens, we'll see. First, if you use only one comparator, then we have to compare this with your tag, original tag. Okay, this is your, let's say, real address. Okay, this is your tag. We have to connect these tag bits to this comparator and we have to compare. Then if you get miss, that means if the output is 0, then we have to connect second tag to here, then again we have to do. But you know, it takes lot of time. If you have, let's say, 100 blocks in the cache, generally the number of blocks will be 2 to the power of x. Okay, it will not be 100. Let us assume 128 blocks. If your cache has 128 blocks, the number of tag fields will be 128 because every block will have tag. Then if you check linearly one by one, then 128 times we have to check. That takes lot of time. Each comparison takes one cycle, let's say 1 clock cycle. 128 such kind of tag comparisons takes 128 cycles. Then what is the purpose or benefit of using cache? Correct? So we should do it parallelly. That means, you know, we have to compare this with this, this with this. That means, see, tag, let us say this is tag 1, this is tag 2, this is tag 3, so on. Tag 1 tag, tag 2 tag, tag 3 tag, everything should be compared parallelly. For that, one comparator is not sufficient. So we will be having a dedicated comparator for everything like this. Okay. Now you see. Similarly, here one comparator like this. So now one comparator here like this. In that way, so this tag is connected to every comparator at a time and checked parallelly. So one of them, if at least one of them will hit, we'll use OR gate. So you get results, right? Result number 1, this is result number 2, right? Comparator result. In that way, all that comparator results will be connected to OR gate. So what happens eventually, really data is available. One of the tag comparator will give you output 1. In the OR gate, one of the output is 1, then you get 1. That means hit. If output of R is 0, that means, you know, no tag matches, then output is 0. Then with one comparator time, we can do it. Understand? But the problem, unfortunately, so you need lot of comparators, then, you know, it will be costly, right? Hardware will become very costly, right? Cost is very much. Direct map technique, in that only one tag comparator is required, then if that will be the cheaper circuit, right? It's a trade-off. But the direct map technique doesn't have flexibility, right? So that means what? You will be getting lot of cache misses. Why you will get lot of cache misses? Recall, already in the cache block someone is staying now, another one wants to come to same location, but there is a space, but because of the direct mapping technique, that second fellow also wants to go here only because his formula says that we have to go here. Then you will not be utilizing the cache properly, then the number of cache misses might be more, right? So that will affect the again CPU performance. So finally, that is the difference between associative mapping and direct mapping. Okay, we'll see the differences again. First thing, that is circuit wise, so that is cheaper circuit, right? Direct mapping. So associative mapping requires lot of hardware, lot of comparators. Number of comparators required equal to number of cache blocks. That is one thing you should remember. Second thing, so that's why, you know, hardware is very costly, right? That you should remember. Now direct mapping and associative mapping, if you see, associative mapping is flexible. You can keep any data anywhere, so that, you know, number of cache misses will be reduced. We'll see with some examples. We'll take one example and we'll see number of cache misses in direct mapping and associative mapping. After that, at that time you will realize why associative mapping generally requires will have less number of cache misses. Very simple. Because example, there is no space here, we can keep here. If there is no space, we can keep here. We are effectively utilizing the cache. But in the direct mapping, you are not doing that. So we'll see with one example. So here, so example, let's say you have 4 cache blocks. 0, 1, 2, 3. Okay, and let's say main memory contains 256 blocks. Okay. Now they are, you know, that 0 to 255. Now the memory references are, let's say 7, 11. These are all block numbers. Okay, main memory block numbers. The current memory references we are getting are 7, 11. Let's say after that, let's say 13. Then later 7. Then, you know, maybe 7, 11, 13, 7. After that, let's say again 11, again 7, again 11. So what will happen, we'll see. The number of cache misses we will see in the direct mapper technique. Okay, let us apply direct mapper technique. In direct mapper technique, what are we going to do? Initially, we will be keeping 7 where? Recall. See, I will tell you one shortcut. Whenever you know the main memory block number in decimal, if you want to know the cache block number where it goes, simply divide that 7 by, you know, that number of cache blocks, okay, and get the remainder. What is the remainder here? 3, right? So that 3 is going to be the corresponding cache block. That's it. So 7 always goes here. Now 11. So that 11 simply divide by 4. The remainder is 3, right? So it will go to same place. But already it is occupied, right? Then we have to keep 11 here. Okay. That will be the right strategy, because you know most recently used one is 11, right? Correct? That's why we have to keep here. So this is called a technique called, you know, least LRU algorithm. Here, whenever you have to replace any data item, whenever, because sir, why we have to replace? Already I told you the major principle of cache is whenever data is not available in the cache, we have to transfer the data to the cache, then we access, correct? So that always we keep the recent fresh data, right, which is most relevant, otherwise most frequently accessed. That's why, so here currently people are accessing 11, then we keep 11, right, 11th block, so that we get the benefit of spatial locality, right? Now after that 13 comes. If 13 comes, then what to do? So far how many cache misses? 7, let me mark it, cache miss. 11, cache miss. Now 13, divide 13 by 4, you get remainder. 13 means 1, right? So this is free, we can keep here. Then after that 7. Now again cache miss, correct? So whenever 7 comes cache miss, then 7 goes here, then we have to remove 11. We don't have option, right? So that way. Then, sir, why don't you keep in this place? In the direct mapping technique, always 7 should go there only, so that we can avoid the search, right? Now 11. Again there is a miss, right? We keep here. So now 11 is here. After that 7, again miss. Though you have space, you are not utilizing it, but you are, you know, getting lot of misses in that way. So since 7 and 11 wants to go to same location, then every time you get miss. Miss, after that, you know, miss, because first time we are keeping, right? After that 7, miss, 11 miss, 7 miss, 11 miss. In that way, everything is miss. Then that's a worst behavior. If it is associative mapping, what is going to happen, we'll see. So no division, nothing. Anyone can go anywhere. So 7 can be kept anywhere. Assume that, let's say we are keeping 7 here. Okay. Now 11, anywhere you can keep here. Then 13, keep here. So 7, keep, so here already it is there. Then hit, right? Now I can say 7. First time when you access 7, miss. Second time, next time when you access 11, miss. 13, miss. But next time when you access 7, it is available. So hit. 11 again hit, 7 hit, 11 hit. So number of misses are only first 3. Understand? In that way, associative memory will associative mapping will have, you know, definitely advantage over direct mapping, but hardware wise it's, you know, costly. Generally that's why people don't use associative mapping. Similarly, people don't directly prefer direct mapping. So there is one more alternative we can go for, that is set associative mapping. We'll see that set associative mapping also. After that we'll decide which one to use. Okay, so it depends on this, you know, designers, like what to use. Just understand pros and cons. After that we can fix it. It depends on our requirement. So we have 3 models: direct mapping, associative mapping, set associative mapping. Set associative mapping is a compromise between direct mapping and associative mapping. It will have, you know, both of the features. Like, what is the main feature of direct mapping? Less hardware, right? What is the advantage of associative mapping? Flexibility, correct? So that, you know, cache hit ratio will be improved, right?